Hello, welcome to another Math Talk. Today we have with us Dhruba Sarkar of B.Math third year. He is interested in algebraic number theory. Today he is going to speak about topological groups and Pontryagin duality. Over to you.
Okay, so today we will talk about Pontryagin duality. And so, what is the essential idea of Pontryagin duality? So, Pontryagin duality is essentially like a Fourier transform in the context of groups. So, as you know, in Fourier transform, all the information that is inside a function is encoded in some integrals. Similarly, in Pontryagin duality, we will look everything that a group has, a locally compact abelian group has all the information. It is encoded inside its dual in some sense. So let me define what a dual is. So then G star, which are write as gamma also, is basically I will need topological group. Where T is essentially the unit circle. So the dual of a group is essentially all continuous homomorphisms from that topological group to the circle. Now, and the topology on gamma is essentially the compact open topology. That is, all subbases are of this form, where U is open in P and K is compact in G. So this is basically so under the compact open topology, we give a topology to the dual, and this is how we define the dual of a topological group. Now, so I have already talked about topological group, but let me define it. So a topological group is essentially a group G with a topology such that the multiplication action, that is G cross G to G, A comma P maps to get P, and the inverse function are continuous. This is the definition of a topological group. And now, just from this definition, we have a lot of things. For example, left multiplication by, let's say, A. That sends x to Ax. This is a homeomorphism. And then we also have things like, this is one thing. The other thing is, if A is a subset of G, U open in G, this implies AU is also open. Why? Because I can write AU as cosets of U. Similarly, if A and B are compact in G, then AB is also compact in G, because continuous maps send compact space to compact space. So we have these kinds of properties in topological groups, and the fact and only these two conditions making the multiplication and inverse continuous, it actually has very strong implications in the context of topological groups. For example, in topological groups, T1 implies T2 implies T3. So why is that? So this is because if we let this map A the inverse, then I can find some open set V cross W which is inside F inverse U for any open set U. So let X belongs to U. So for any open set U, I can find V comma W such that X comma E is in this. So this would imply V intersection U complement W is empty. Why? Because if anything is in the V intersection U complement, I can just take the F map and fill again and in U. I just take the inverse of the W map and then one can easily check this. So because of this, and also because E is inside W, U complement is inside U complement W. And from this thing, we have U complement W is open, and V is also in. So this would imply X is in V, which is inside U complement W complement, which is inside U. And this is a closed set, so this implies X belongs to V, which is inside V bar, which is inside U. So just T1 implies T. So we are assuming that X is so from there we choose a suitable U and then so then we also have some more things like if H is a subgroup of G, then so is the H closure. Similarly, we have properties like if N is normal in G, so is N closure. And then we also have the property that the projection map from G to G mod N, where N is normal in G, is an open map. So why is this? Because I can just take P inverse PU. This will just be NU, which is again open because of because of that care that U is open, so NU is open, so this implies PU is open for any open set U. So you have a lot of these conditions, and you also have the fact that G mod N has discrete topology if and only if N is open. Why? Because I can take the pre-image of each singletons, and since N is open, the pre-images will also be open because the pre-images will just be cosets of N. So we also have this thing. So now we can look at a version of open mapping theorem in the case of topological groups. So before that, we would need something called Baire category theorem. Now I think some of you might not know about Baire category theorem, so let me prove it real quick. what Baire category theorem says? It says that if X is locally compact Hausdorff space, then X is not a union of countable collection of closed sets which are empty, which has empty interior. So this theorem might seem very arbitrary, but it has a lot of applications throughout topology. As you'll see, even in this talk, we'll use it to Open Mapping Theorem. You can prove other versions of Open Mapping Theorem in analysis using Baire category theorem. So, countable collection of closed sets what we are essentially interested in Baire category theorem is the main thing that helps is if I can write X as a countable union of closed sets, then Baire category theorem says at least one of them has non-empty interior. So that is actually very useful in topology, in functional analysis, throughout mathematics. So what is the proof of this? The proof is that suppose X is equal to union of n such that each of them has empty interior. So let we define Dn to be the complement of An. So because each An has empty interior, each Dn is dense in X. So because X is locally compact, I can find a U0 such that a U0 open such that U0 bar is compact. And since each DL is open and hence U0 intersection D1 is non-empty, so similarly I can find U1 bar which is inside U0 intersection D1. Yeah. Because X is locally compact, I can always find this. And inductively, I can find Un plus 1 such that the closure is inside Un intersection Dn plus 1. Right. Now, since U0 bar is compact, bar is non-empty because of the finite intersection property of compact spaces. So this implies intersection of Dn is non-empty. So hence we arrive at contradiction. So hence at least one A must have non-trivial, non-empty interior. And now prove something called Open Mapping Theorem, and this Open Mapping Theorem in the context of locally compact groups would help us immensely in our proof of Pontryagin duality. So what is Open Mapping Theorem? So Open Mapping Theorem says G be locally compact group such that G is sigma compact, or equivalently I can write G as the union of AN such that each AN is compact. So I can write G as the countable union of compact spaces. Then if we have a map from F from G to H, which is continuous and onto where H is a locally compact Hausdorff sprue, then F is open. So pretty strong here with some pretty strong assumptions also. And let's prove it. So first, let U be a family of symmetric neighborhoods of E in G. Symmetric means if let's say V is an element in U, then V is equal to V inverse. You can always construct it because multiplication and inverses are continuous. So G, and similarly let U dash also be a family of symmetric neighborhoods of E in H. and then because multiplication is what do you call it? Because multiplication is continuous, so I can just shift my u bar so that for each element I can find a small enough u bar in Fu. So this is fine. So let's see. Now since it is locally compact, q will q bar q dash. So because it is locally compact, there exists V in U such that V bar is compact and V bar inverse V bar is inside V. Then if we look at XV, this is an open cover of G. Now since G is sigma compact, I can write G as countable union of X and V. Like now since F is on 2, this implies H is equal to F of G, which will be equal to countable union of Fx and Fe, which will again be inside of so H is equal to this. Now we can use Baire category theorem to say that at least one of them will have empty interior. Non-empty interior. But as you can see, if at least one of them has a non-empty interior, I can just shift by Fxn. So F V bar will already have a non-empty interior. So I can just let V dash be inside F V bar, and which will be inside F V bar inverse F V bar. This is equal to F V bar inverse V bar, which is equal to F V, rather than inside F V. So hence we have found the V dash such that which is inside F V. And this concludes our sheet. Okay, so till now we have introduced topological groups and seen some of its properties, more or less. So next we would look at some properties of R in general. We'll look at R and R unit circle. So the proposition says non-discrete subgroup of R is dense. And the proof is also not hard. So the proof is essentially, let's say G be a subgroup of R, and since it is non-discrete, there exists X belongs for all epsilon positive. There exists an X in G such that X is in this. Why? Because it is not discrete. 0 is not an isolated point. So I can find elements arbitrarily close to 0. And now we can see that the set of these intervals cover R, and the distance between and the length of each of these intervals is epsilon. So if I take any 2 epsilon interval, at least one NX would belong. So for any 2 epsilon interval, my G intersects is non-trivial. So hence we get that if a subgroup is not discrete, it has to be dense. And this gives us some things. They will be important in the proof of Pontryagin duality. Is that R is closed, then G equals to R, or a discrete subgroup of this one. And this also says that if you have a non-trivial house, the quotient group of R, is isomorphic to the unit circle. So why is it? If you have R mod some G subgroup, since R mod G is house of, the preimage of 0 here will be G itself, and the preimage will be closed. So my G is closed. So G is either R or AZ. If it is AZ, then R mod AZ is just R mod Z, which is just a unit circle. And then this also shows that every proper closed subgroup of T is finite. Why? Because I can write T as R mod Z, and and just look at the pre-image of the closed subgroup, which will again be of the form R or AZ, because it is proper, it is of the form AZ. And now we go back to the image and it will be finite. So and there is one more fact. This is not related to this proposition, but just if G is closed subgroup Rn, then G is just R to the power A, Z to the power B, where A plus B is less than N. The proof is essentially you take open balls and you look at elements of G as vectors in Rn, and you keep on shrinking the open balls and you see what happens to the rank. The rank will stabilize after small enough shrinking. So that will give you your A, and because it is closed, it will already contain the entire R. And then you look at everything outside of it, it will be discrete, and hence from there you will get Z to the power B. I said it in a very hand-wavy way, but you can fill in the details. And finally, we need a final proposition. Says that if B is a divisible group, a divisible group means if X belongs to D for all n in Z itself, there exists Y belongs to D such that Y to the power n equals 6. So this is the definition of a divisible group. So essentially you have all the roots of an element, of each element inside D. So and let's say H is a subgroup of G for any group G. Oh, we didn't opinion. And divisible abelian. Then every homomorphism from H to E, there exists gamma tilde from G to D such that gamma tilde restricted to H is just gamma. So basically what we have is we have a map gamma from this to D. We have inclusion in G. We can find this gamma tilde. This gamma tilde need not be unique. So the proof essentially uses Zorn's lemma. So for applying Zorn's lemma, we need to find that if X does not belong to H, then if we let H dash to be the subgroup generated by H and X, then can we lift this gamma to H dash? So that will essentially prove it. Case 1. The subgroup generated by X and H is empty. Then I can define my gamma tilde from H dash to D as gamma tilde of H to the power n as gamma of H. And you can check that this is well defined, this is a homomorphism, and this satisfies the lifting property. And if you look at case 2, non-empty let MB smallest such that x to the power n belongs to H. Right? So let's say h to the power n equals H. Define my gamma tilde from H dash to D by gamma tilde of X equals to 1 by n, that is m inverse of gamma of H. And then for gamma tilde of H, it's same as gamma H, and then you can also check well definedness for this one. And hence you can lift your gamma from H to H dash, and then you can just use Zorn's lemma to get a maximal element, which will again be the entire group G itself. So this is done. So now we can finally start proving Pontryagin duality. So before just starting it, we will now prove Pontryagin duality for compact and discrete groups, and then we will slowly move towards a more general conclusion. Let me write here what is Pontryagin duality. Pontryagin duality says that let alpha be a map from G to gamma star given by alpha of G equals to Fg, which is a map from gamma to P, which maps gamma to gamma G. This is an evaluation map. Then if G is Compact Abelian. I will abbreviate it to LCA. Group. Then alpha is a topological isomorphism. That means alpha is continuous and then isomorphism has groups. In fact, what we'll show is alpha is in fact an open map. So this is my Pontryagin duality. So let's talk about compact and discrete groups. So we can show that if G is compact, gamma is discrete, and if G is discrete, my gamma is compact. So the proof is not that hard. So let's say if G is compact. Then you just look at this open subset of gamma. Where this is your P. B is something like this. This R can, let's say, this is B. So now, as you can see, every element in gamma is a homomorphism. It should send G to a subgroup of P. But as you can see, the only subgroup of P in VA is the trivial subgroup. So this is just this singleton G. That is the zero map. So this implies gamma is discrete. So now if G is discrete, then I can look at this, and this will be compact because, well, I would need one assumption here that if G is locally compact abelian, then gamma is also locally compact abelian. The proof is a bit long, but it is fine. So if we assume this, then we can say that this is compact for small enough VA. So we can take VA small enough such that this becomes compact. But as you can see, this is essentially my entire gamma. Because obviously every gamma sends 0 to 0 inside this VA. So hence gamma is compact. Right, so let's look at some examples of compact and discrete group. So the two most trivial examples are my unit circle, which is the compact group, and my set, which is the discrete group. So let's see. So what I'll show is D star is just Z. So let's say gamma be a map from T to T, from the unit circle to the circle. Then kernel of gamma is closed, implies gamma is cyclic. Kernel of gamma is cyclic, implies cyclic. So let order of kernel of gamma be equal to n. Then we can have a map. So we have T to gamma T, and then we also have the projection map T mod kernel of gamma. And now since kernel of gamma is cyclic and it will be finite also because we already showed it, this will again be isomorphic to T. So let's call the isomorphism theta. So I can find an isomorphism alpha from T to T such that this entire thing commutes. And now note that since order of kernel of gamma is m, theta of T of x is just x to the power n. And finally, you can show that since alpha is a continuous isomorphism from T to T, alpha x is just x or minus x. You can use it. What you can do is you can keep on taking these square roots of elements. So, for example, alpha of -1 should be a square root of 1, which will again be -1 because alpha is bijective. Now you look at alpha of I, it will again be a square root of -1. You have two options, I and minus I, and you keep on doing this. So you will exactly know what the dyadic rationals map to, and from there you can use the compactness property to get alpha x equals x or minus x. And because this entire thing commutes, from here we get gamma is just alpha of theta p of x, which will just be whatever x inverse. Gamma will just be gamma of x is just x to the power n or x to the power minus n. So from there I can take a map sending gamma to m, sending each gamma to n. This will be algebraic homomorphism, and because and then I can just take modulo with respect to the kernel, it will again give you Z. Sorry. Oh, and this will again be on to. So from there you will get T star is isomorphic to Z, because for every m I can find the suitable gamma so that is solution. And then the other example is essentially with Z. So why is that? The proof is essentially that if you have a map from your homomorphism from Z to T, it is essentially determined by wherever gamma 1 goes. So you can just this completely determines this gamma, and now you can check that this is continuous, this is a homomorphism and everything. So from there we get this. So from here we can now see that my Pontryagin duality would hold for T and C. But anyways, we need to prove it for in generality. So let me alpha in the Pontryagin duality is a continuous homomorphism. So let's prove this. So what we have to show here, we just have to show that for all A compact in gamma and the epsilon open in T, there exists a neighborhood of 0 in G B such that alpha of B is inside my P K B epsilon. So we need to show this, which essentially means that for all G belongs to B, gamma G belongs to D epsilon for all gamma belongs to P. Right, so we need to show this. We need to find a suitable V such that this holds. So let U be an open set containing identity such that U bar is compact. So this implies K is in gamma belongs to gamma. K is in the set of all these open sets, because this open set covered the entire gamma, so K is in this. So this implies K is in finitely many of them. And now we can let U1 to be U this will be open because each gamma i's are continuous. So we claim that this U1 works. So let's see. When gamma belongs to K, this implies gamma belongs to gamma I plus B U bar comma B epsilon by 2. Right. This implies now G is in U1. This implies gamma minus gamma 1 gamma I of G belongs to B epsilon by 2. And what does this imply? This implies gamma of G minus gamma I of G is in an epsilon by 2 ball. But we know G is also in the pre-image of gamma I of an epsilon by 2 ball. So this implies gamma of G belongs to B epsilon by 2 plus B epsilon by 2, which is inside an epsilon ball. So hence we are done. Since G and gamma are arbitrary, we are done. And next we'll look at how continuous homomorphisms affect maps from their corresponding gammas. So if homomorphism then I have the usual map F star from B star to A star. That is, if I have a continuous map from B to T, I can extend it to a map from A to T. So this is that map. If F is on to F star is 1 1. If F is open and 1 1, F star is on. So how do we prove this? The proof is also essentially, let's say, so first we want to show that F star is continuous. Continuity is not an issue because you take F star inverse of A comma B epsilon. This is essentially P of F of A comma B epsilon. Why? Because it says what are those gammas such that gamma of F of K is inside B epsilon, which is essentially this, the thing on the right hand side. F star is continuous. So let F be on 2. Then let's say F star gamma 1 equals F star gamma 2. This implies gamma 1 f of x equals gamma 2 f of x for all x belongs to A. But since f is onto, this implies gamma 1 equals gamma 2. So we have this, and now let's assume if f is open and 1 1, then delta belongs to A star. So what does this mean? So I have something like this: A to T, but delta, and this is my inclusion map F, A of A in B. Now because T is divisible, I can use the proposition that I proved earlier to find a gamma. So there exists a gamma such that gamma of F is delta. Now this gamma is just a homomorphism. We don't know for sure if it's continuous or not. So for every delta in A star, we have found the gammas, not necessarily a continuous homomorphism, such that gamma of F is delta. Now since F is an open map, this implies gamma